The first classification we have already discussed, that is the based on the classification of signals based on the independent variable, that domain of the function, that is continuous time and discrete time signals. Okay. Continuous time signal and discrete time signal. Continuous time means the independent variable is a continuous variable. Here we consider t, and this is a discrete variable. That is the first classification based on the independent variable of that function. And the second classification is odd and even signals. So that is classification based on the symmetry property of that signal. When can we say that a signal xt is even? Signal, when is the function xt is even? Is it this?
V equal to x of minus
X of minus t. Then we can say that the signal is that signal is even. Okay. And when xt is equal to minus x minus t, then it is an odd signal. And you can visualize this also. What does it mean in terms of the shape of the signal? Even signal means what? This is an even signal, isn't it? It is symmetric about the y-axis. That means if we flip the signal, about the y-axis, you should get the same signal, isn't it? That is the even signal. So it is symmetric. We can say that even signal is symmetric about the y-axis, and odd signal. Let's say this is an example of an odd signal. It is anti-symmetric about the y-axis. If you flip the signal about the y-axis, you will get the negative of that signal. That is an odd signal. So this classification is based on the symmetry. Okay, one thing you have to keep in mind is when you say that xt is x minus t, this should be valid for all the values of t. Okay, these conditions must be valid for all the values of t. Then only we can say that it is an even or odd signal. For example, if you consider this signal, let's say this is a signal. Is it an odd signal or even signal? Neither. You cannot say that. The reason why I am stressing on this point is it should be valid for all the values of t. Then only we can make this classification. We cannot say that it is even in this portion and this part is odd. No. If it is satisfied for all the values of t, then we can say that it is an even signal. If it is if this condition is satisfied for all the values of t, then it is an odd signal. Okay. Now, if you are given, you must have studied in your mathematics course that if you are given any function xt, you can always write it as a sum of an even function and sum of odd function, isn't it? Okay. So in the case of signals, if you are given any signal xt, we can express that signal as the sum of an even signal and an odd signal. Now, how to get this xct and xot? Xct is the even part of the signal and xot is the odd part of the signal. How to get these two? What is x
So
of
we can mirror.
what is x of minus t? Replace t with minus t. What will happen here? The first term? Xe of t, because this is an even signal. Xe of minus t is xe of t only. And what about the second part? Is it minus? Is it this? I'm replacing t with minus t. I have skipped the intermediate step. Intermediate step is x minus t is xe minus t plus xo minus t. And since this is even and this is odd, we can get this. Okay. And from these two, what is the even part of the signal? Is it xt plus x of minus t by 2? Is it that? Even part of the signal? Add these two, divide by 2, you will get xet. And xot is xt minus x minus t by 2. That is the odd part of the signal. Okay. Let us consider an example. Let's say this is a signal 0, minus 1, 1. It is minus 2, 2, and 2. Okay, this is a signal xt. Is it an odd signal or even signal? None. Okay. Now, can we find the even part of the signal? What is the even part of the signal? Okay, so how to get the even part of the signal? It is xt plus x minus t by 2. What is the reflected signal here? Is it this? This is the time reflection operation. Now, if you add these two signals, what is the signal? Xet, even part of that signal. What will happen? Let us consider this first. In this interval 0 to 2, this is the signal. We have to add these two signals. So can we say that this is a constant value 2? We are adding, if we are add these two, if we add these two signals, can we say that this signal, the operation is that this signal is shifted up by 2? Is it that? This is a constant value. We are adding a constant value to this part of the signal. That means it will be shifted up by 2. So this will be this. And do we need to calculate this part? Because anyway, xet is an even signal. So it must be a symmetric. It must be symmetric about the y-axis. So is this the even part of the signal? And what about the amplitude? What about this value? Hello. This is 2 or 1? Because there is a scaling factor. You have to divide by 2. Okay, this is 2 and this is 1. Is it? Now, what about the even part of that signal? Sorry, odd part of the signal. You have to subtract the signal from this. So what is it? Can you tell me what is the shape of that signal? Let us consider this part. If this is constant 2 and we are subtracting this, so will you get this? Is this a signal? Positive for positive values of t? Yes or no? Hello?
Yes.
This is a signal. Now negative part, anyway, you don't have to calculate it because this is an odd signal. So it is the reflected version of this. This is a signal. So if you can verify that if you add these two, you will get this. Will you get that?
So odd function will come down.
Sorry?
reflected below the x-axis.
Yeah, sorry.
This is so origin.
This is this is odd signal. So it is okay. If you add these two signals, you will get this. Okay. That is how we find the even and odd parts of a signal. If you are given any signal, you can express it as a sum of even signal and an odd signal. And if the signal xt is even, then what will happen? What about xot? If xt is even, what is the odd part of that signal?
Null function.
It is 0. It is odd, that is 0. Okay. And if xt is an odd function, then even part of that signal is 0. Periodic. What is a periodic signal? Periodic signal. When can we say that a signal is periodic?
It repeats after a certain time period.
It repeats that pattern repeats after a certain time period, isn't it? So for a continuous time period, continuous time signal, we can write a periodic signal as xt plus t naught. Let's say, and this is for all the values of t. That means that pattern repeats after every t naught second. Let's say t naught seconds. So this t naught is called, the minimum value of t naught is called the fundamental period of the signal. Minimum value of t naught for which this condition is satisfied, that is called the fundamental period of the signal. Okay, so now for a discrete time signal, if this condition is satisfied for all the values of n, then it is a periodic signal, and the minimum value of n that satisfies the this condition, that is called the fundamental period. And this condition is very important for all n and for all t, because if you consider if you generate a practical let's say a practical sinusoidal signal, if you generate in the laboratory, it is a finite duration signal, isn't it? We generate a sinusoidal signal for a finite duration. That is not a periodic signal. We cannot say that this signal is periodic in this period and it is a periodic outside that period. It is not that. This condition must be satisfied for all the values of t. Then only we can say that the signal is periodic. So can we say that all the periodic signals are everlasting signals? They starts at minus infinity, and it is going up to infinity, isn't it? They are everlasting signals. They are not physically realizable signals. Okay, they are not physically realizable signals. Now, if we let us consider some properties of this periodic signals. If we consider two periodic signals, let's say x1t and x2t, the first one is having period t1 and the second one is having period t2. What about x1t plus x2t? Will it be periodic?
Yes, sir.
Will it be always periodic?
Yes, sir.
Yes?
If they have LCM only.
If they have LCM, then it will be periodic, isn't it? Okay, let us draw two signals. Let's say this is the first periodic signal and this one is the second one. Okay, so two periodic signals. This one is this is one period. Let's say this is t1 and this is t2. So what is the condition for the sum of these two to be periodic? Means let us consider this point. At this point, sum of these two signals is sum of this plus this. And if it is periodic for some periodic with some value t naught, then that condition is that at that t naught, the sum should be same as this, isn't it? Then only it is a periodic signal if it is satisfied for all the values of t. Now, what is that condition? If the sum is periodic with the period t naught, then these two signals, they should also be periodic with that signal, that period, isn't it? T naught. Is it that?
Yes, sir.
But their periods are different. One is t1 and the other one is t2. So can we say that this condition is, let's say, m times t1? Is it that? That is equal to t naught, some t naught for some t naught. Is it,
Yes, sir.
is it the condition? So this is the condition for periodicity. If this condition is satisfied, or we can say that t1 by t2, it is a rational number. If it is a rational number, then it is periodic. Otherwise, it is not periodic. If the fundamental period, if this t1 by t2, if it is a rational number, then it is periodic. Otherwise, it is not periodic. And what is the fundamental period? If it is periodic, then what is the fundamental period of that signal?
T naught.
Sorry, t naught is what? What is the minimum value of t naught? Is it the LCM of t1 and t2?
Yes.
So if it is periodic, then it is LCM of t1, t2. That is the fundamental period of sum of two, sum or difference of two periodic signals. Now, what about a discrete time signal? Let's say the first signal is x1n and x2n. This is n1 and n2. What about x1n plus x2n? Will it be always periodic? x1n plus x2n. Is it always periodic? Hello?
Yes, sir.
Is it always periodic or not?
Yes, sir.
Yes means what? Periodic.
Yes.
It is easy to verify because n1 and n2 are integers. Discrete time signal, these periods are integer values. So their ratio is, it is a rational number, right? Ratio, if you take the, what is the condition for sum of two periodic signal to be periodic? Their ratio, that must be a rational number. Since these two are integers, that condition is always satisfied for a discrete time signal. So sum of two discrete time signals, sum of two discrete time periodic signals is always a periodic signal. Okay. Okay, that is another classification, and next classification is based on energy and power. If we consider a symbol, let's say I is the current flowing through this resistor, and so this voltage is, let's say the voltage across the resistor is V volts. Now, what is the power dissipated in this resistor? Hello.
So
It is VI, that is equal to I square R, isn't it? That is the average power. Now, if we consider this as a time varying signal, let's say here we assume that it is a constant current. If it is a time varying current, IT, and this is VT, then we can say that the instantaneous power means the average power at any particular instant of time. So that is I square T R, sorry, yes. Okay, VI is, okay, I square TR, that is equal to, that is instantaneous power, isn't it? So in electrical systems, the signal that we represent, that may be a current signal or a voltage signal. So the standard convention in the signal analysis is that for finding the energy and power, we take R equals 1. So in this case, the instantaneous power is, if R is 1, then I square T or V square T. The advantage of using this convention is that if this given signal xt, if it is irrespective of whether it is a current signal or a voltage signal, the instantaneous power of the signal is x square t. That's why we take R equals to 1. Okay. So this is the instantaneous power of the signal. Now what is the average power of the signal? Or what is the, let's say this is a signal xt. What is the average power? Average power means how to find the average power? Since xt is a function of time, it is varying with respect to time, then how to find the average power of that signal? If we can, we have to average across the time, isn't it? If we consider, let's say I am taking minus t to t. So what is the average power in this interval? It is 1 upon 2t integral minus t x square t. Now the power of this signal, average power of this signal is limit t tends to infinity, this one, isn't it? This is the average, time average power. Now what about the energy of the signal? Is it the energy?
Yes.
That is the energy. Okay. And one more thing, this is for a real valued signal. If we in general we consider complex valued signals. In the case of complex valued signals, the instantaneous power is mod xt square. Okay. This is for real valued signal, and if it is, this is a general expression, mod xt square. Now we can classify signals based on this, the power and energy of the signal. If the average power is finite, then it is called a power signal. And if the energy of the signal is finite, then it is called an energy signal. Okay. Now, can you give some examples of this power signal? First, let us start with the energy signal. Can you give example of an energy signal? Any signal that is having finite energy. If you consider any finite duration signal, what is finite duration signal? If it is non-zero only for a finite duration, is it an energy signal or power signal? It is non-zero only in this interval. Is it an energy signal or power signal? It is an energy signal. The energy is finite, isn't it? So can we say that all the finite duration signals having finite amplitude is always an energy signal? Is it true?
Can you repeat what you said?
No, what I'm saying is this is a finite duration signal because it is non-zero only in this interval. This is an energy signal because if you find the energy of that signal, that is finite. Okay. My question is, can we generalize this? Whether all the finite duration signals having finite amplitude, they are always this energy signal or not?
But not necessarily.
Can you give a counterexample?
Sir, if the signal extends to plus infinity or minus infinity,
No, that's
it
what.
will have.
No, that's what I'm saying. Finite duration signal. Yeah, are you talking about the amplitude? Hello. So we can say that all the finite duration signals having finite, if the amplitude is finite, then it is an energy signal. Now, what about signals? Those are not finite duration. For example, let's say an exponentially decaying signal. For example, discharging of a capacitor. But what about this? Is it a finite? Is it an energy signal?
Power signal.
Is it power signal?
Sir, it is energy signal.
It is energy signal.
Energy signal.
It is energy signal, isn't it? It is energy signal because if you calculate this, that is finite. It is an energy signal. Now, what is the average power of an energy signal? What is the average power of an energy signal? Average power is limit t tends to infinity, let's say 1 to t. This is the average power. Now, can we write this as if this is finite, we can write it. If this integral is finite, if this is minus infinity to infinity x square t dt, if it is finite, then we can write like this. This is the relation between the average power and energy. Is it? Now, my question is, if a given signal is energy signal, what is the average power of that signal? It is zero because energy signal means this is finite and this is averaging over an infinite interval, isn't it? So this average is always zero. So we can say that the average power of an energy signal now can you give example of a power signal? Average power is finite.
Periodic signals.
If you consider any periodic signal, this is a periodic signal. This is a power signal, isn't it? Because it is periodic. So we can say that the average power is the our means if you consider the entire duration, that will be same as the average power in one period of that signal. So this is a power signal. Now what will be the energy of a power signal? Energy of a power signal.
Infinite.
It is
Infinite.
infinite. Isn't it? Energy of a power signal is infinite. So from this definition, we can say that a signal cannot be both energy and power signal, isn't it? Is it possible? If it is having finite energy, then the average power is 0. And if the signal is having finite average power, then the energy is infinite. So a signal cannot be both energy signal and power signal. Okay. Now, is it necessary that this signal have to be periodic for it to be a power signal? Is it necessary? What about this signal? Is it an energy signal or power signal?
Power
It is a
signal.
power signal. It is not necessary that the signal has to be periodic. Okay. And another example is the signum function. This is called the signum function. Anyway, we'll discuss about these different signals later on. This is another example of a power signal that is not periodic. Okay. Now, can you give example of a signal that is neither energy signal nor power signal? Sorry.
Exponentially increasing function.
Exponentially increasing function. It is not a power signal and also not an energy signal, isn't it? And if you simple example is a ramp function, linearly increasing, that is also here it is not a energy is both energy and average power are infinite in this case. So they are not they are neither energy signal nor power signal. Okay.